Hello and welcome. In this video, we're going to be taking a look at a special technique for optimization in multivariable calculus. Now, that's not the first time I've said that at the beginning of a video, so you might be wondering what is different about this technique versus what we've already seen in previous videos. So maybe a quick recap. We know how to find local extreme values already by classifying critical points of a function using the second partial derivatives test. Then, in another video, we took a look at extreme values over a closed and bounded set in Rn. Then we can apply the extreme value theorem and we can actually find absolute extreme values in that same region. Now, we're going to be taking a look at finding extreme values again of a function of multiple variables, but this time with a specific constraint that comes in the form of an equation. Not a region necessarily, but that equation could be a curve or it could be a surface, depending on how many variables we have. That allows us to apply a pretty special technique called Lagrange multipliers. And it's a nice way to kind of take everything we've learned about the gradient, level curves, apply that so that we can just find the values that give a maximum or minimum using just a bunch of equations that we can then hopefully solve. So let's take a look. We're going to be taking a look at constrained optimization in this particular form, where we're looking for the minimum or maximum values of some function of n variables. We'll call that our objective function, and we will have at least one constraint, but potentially more, and the constraints will be in the form of some implicit function in this form g of x1, x2, all up to xn equals a constant k. Now I find that it is probably best to start with an example in two variables that we can easily visualize on the xy plane and see how this method works visually. So let's tackle this example. Let's try to find the minimum value of the function f of xy equals x squared plus y squared, where xy has to be a point specifically on this curve xy squared equals 16. Right away, we should at least name these two functions. Our first function, f of xy, that's our objective function. That's our goal, is try to make f of xy equal to the minimum value possible. And this curve, xy squared equals 16, well, we can picture that as a function as well. We can let g of xy be xy squared, and in this case, g of xy has to equal 16. Now, first of all, let's see what that curve looks like. Now, that curve is kind of an interesting looking curve. For a given value of x, say x equals 4, then we would have two different values for y, since we have xy squared. Y could be both positive or negative. And that's why we have this nice symmetry over the x-axis. Now, the goal here is to try to get f of xy to be a minimum. So essentially, we want f of xy to be some value c, where that value of c is a minimum. And let's just take a look at the curve defined by x squared plus y squared equals any constant. And you should hopefully recognize that that would be the equation of a circle. For any given value of c, if we have x squared plus y squared equal to c, we can actually sketch that graph. And it's a circle of radius square root c centered at the origin. Now the method that we're going to be applying here is really just treating f of xy equal to c as the level curve of some kind of surface in R3. Now, if we're treating f of xy equal to c as a level curve, remember that the gradient of f points in the direction of maximum rate of change of the function, and it's always orthogonal to the level curve. In this case, as c is increasing, the radius of this circle is increasing. So at these points here on the curve xy equals 16, our gradient is going to be pointing orthogonal to this circle and away from the origin. Now remember, we're looking for a minimum value of the function f. That means that we should be moving from these particular points here that all have the same value of that objective function and trying to move in the direction of the negative gradient of f. And so you can kind of see that tells us we want to move this point closer to the origin. That's pretty easy to do. X squared plus y squared equals c is a circle centered at the origin, and we just have to decrease c a little bit. That's essentially shrinking the radius. And that should move these 4 intersection points a little bit closer to the origin. Now, that's a little bit hard to see visually, so I've set up an animation here in Desmos for us. And you can see I've got the graph of xy squared equals 16, that's this red curve, and I've got x squared plus y squared equal to k, where right now k is 36. And you can see the 4 intersection points there of the blue circle and our red constraint. Let's start shrinking k down, and you'll see that the radius is decreasing, and the 4 intersection points are all moving closer to the origin. We're moving in the direction of the negative gradient of f, until eventually you can see that we get to k equal 12. And if we go beyond that, you can see that our function no longer intersects the constraint, and there are no points on our constraint curve that satisfy our function f of xy equal to 11. So it looks like our minimum distance must be 12, and we can see that there are really only 2 points that give us that minimum value. What's more important to note here is that the 2 curves are tangent to each other, or that they share the same tangent line. And that's the basis for this method. So let's go and explain that back in the notes here. As we saw in Desmos, when the function f of xy is at a minimum along that curve, in this case xy squared equals 16, then the 2 curves are tangent to each other, or they share the same tangent line. Now remember, we're treating f of xy equal to c as being the level curve of a surface, and we're using the gradient to tell us sort of which direction to go. The gradient of f is orthogonal to this tangent line that both curves share. At the same time, our constraint xy squared equals 16, we can also treat that as a level curve, g of xy equals 16, in which case the gradient of g is also orthogonal to that tangent line. Well, in 2 dimensions, if we just have a tangent line and the gradient of f and gradient of g are both orthogonal to that, that tells us that the gradient of f must be parallel to the gradient of g. That means one gradient vector is a scalar multiple of the other. The gradient of f could be written as lambda times the gradient of g for some constant lambda. We call that the Lagrange multiplier, and that is the key to this method. Now the next thing here is that one equation involving gradients can actually be split up into 2 separate equations. fx equals lambda gx, and fy equals lambda times gy. There's 2 equations right there, plus we already have the equation that xy squared has to equal 16. Now we're trying to solve for x and y that give a minimum, but we've just introduced lambda, so there are 3 variables. 3 equations, 3 variables. It seems like we should be able to solve this system. In this example, to get a minimum, fx must be lambda gx, fy must equal lambda gy, and xy squared must equal 16. Since our function f is x squared plus y squared, then this first equation turns into 2x equals lambda times y squared. And our second equation, 2y equals lambda times 2xy. And that constraint equation, we can leave it as is. That's our third equation. Now let's see if we can solve this system. And I would suggest starting off with what might be the easiest one to factor. I'd say probably starting off with equation 2 is the best option here. 2y minus 2 lambda xy equals 0 is something that we can easily factor so that we can use the zero product property. If we factor 2y out of both of those terms, that leaves us with a factor 1 minus lambda x. That leaves us with 2 options to get a zero product. Either y equals 0 or lambda x equals 1. Now this first potential value here, y equals 0, is impossible because of equation 3. There's no way that that could potentially be a solution to the full system of equations, so we can throw that one out immediately. This second option is our only potential way to solve the system of equations. maybe we should just rewrite that as lambda equals 1 over x so that we can substitute into either equation 1 or equation 3. But equation 3 doesn't have lambda in it, so I guess we're going to be sticking to equation 1. Plugging that in for lambda, we get 2x equals 1 over xy squared, which gives 2x squared equal to y squared. Well, that's good news because we have y squared in equation 3. Now we can replace that with 2x squared and solve for x. And that gives us x equal to 2. Once we have x equals 2, then we can trace our steps backwards. We can see that 2x squared has to equal y squared. That tells us that 8 must equal y squared, and y can be plus or minus root 8, which simplifies to plus or minus 2 root 2. And if we so desire, we can even solve for lambda by going up a little bit higher. If lambda equals 1 over x, then lambda must be 1/2. That gives us the 2 points that we saw in Desmos. The coordinates of those points are x equal to 2 and y equals plus or minus 2 root 2. Now, what about that minimum value? If we plug both of these points back into the original function f, which was x squared plus y squared, then we see that we get the value of 12. And that corresponds to what we saw in Desmos when we shrunk that circle down to the smallest possible value. All right, now that we've seen the method visually, let's actually write this just in terms of f and g being functions of multiple variables and see the particular process that we have to follow in order to find minimum and maximum values subject to some kind of constraint. For the method of Lagrange multipliers, we're going to be focusing just solely on optimization problems where we are maximizing or minimizing a given function, and maybe let's say a function of 3 variables, f of x, y, z. We call that our objective function, and we'll have some kind of constraint of the form where g of x, y, z equals k, where k is a constant. Then our method says, step 1, find all values of x, y, z, and lambda that satisfy the system of equations gradient f equals lambda gradient g. That just tells you that the two gradient vectors are parallel. And another equation, g of x, y, z equals k. That's literally just a constraint. Now, once we find points that satisfy that, we can evaluate f at each of those points to find a maximum or minimum. Now, for simplicity, we can actually turn the whole system of equations here into a single equation that we might find easier to remember. We can define a function that we call the Lagrangian. Now, if our functions f and g are functions of 3 variables, x, y, z, the Lagrangian is a function of 4 variables, x, y, z, and lambda. And the whole system of equations can actually be just summed up as just being the gradient of the Lagrangian function must equal the 0 vector. And the way we always set it up is by simply having the objective function, f of x, y, z, minus lambda times our constraint in the form g of x, y, z minus k. Now let's try a practical example using the Lagrangian, and you'll see how setting the Lagrangian equal to the 0 vector is equivalent to setting up this original system of equations for the method of Lagrange multipliers. Now let's try a practical example here. Let's see if we can design a right circular cylinder that will give a minimum surface area but still allow a volume of 500 milliliters. Now, you can imagine that we're maybe trying to design something like, the optimal beer can, where it minimizes the amount of materials involved to actually construct the can, be the smallest amount of aluminum, but still has to have the correct volume. So obviously, a little more applied than some of the other optimization problems we've looked at in the past. In this case, what we're trying to minimize is surface area. And we might want to take a look at what a right circular cylinder looks like here for a moment. We've got a top disk and a bottom disk, as well as one lateral surface. The areas of the top and bottom are both pi r squared, and the area of the lateral surface is 2 pi r h. If we add those together, we get our objective function. F of r comma h is going to be 2 times pi r squared plus 2 pi r h. We're minimizing that, and our variables are r and h. Our constraint is the volume of the can, and the volume is the area of the base times height, so that would be pi r squared h. That's our function g, and we need g to equal 500 milliliters, or 500 cubic centimeters if that helps us to get units of r and h. Now, right away, we could go ahead and set the gradient of f equal to lambda times the gradient of g, and have our third equation being pi r squared h equals 500. But let's try setting up the Lagrangian. The Lagrangian is going to be a function of three variables, r, h, and lambda. And we'll have our objective function minus lambda times our constraint in this implicit form. Now we can set the gradient of the Lagrangian equal to 0, and we get three equations out of that. These three equations will be the three first-order partial derivatives of the Lagrangian. That first one, if we're taking the partial derivative with respect to r and setting it equal to 0, will give us 4 pi r plus 2 pi h minus 2 lambda pi rh, all equal to 0. Now, it's going to help us probably at some point in time to try to factor this, and maybe right off the bat we could try to factor a common 2 pi out of that whole left-hand side. Our second equation will be the partial derivative of the Lagrangian with respect to h, and we'll set that equal to 0. That is 2 pi r minus lambda pi r squared. And that's an easier one to work with probably. Let's factor that right away as well. We have a common factor of pi r, and that leaves us with 2 minus lambda r. Now, for equation 3, we take the partial derivative with respect to lambda, and that's going to eliminate these first two terms and leave us just with minus 1 times everything in those parentheses. And you'll see that right away, we can drop the negative sign by multiplying both sides of the equation by -1, and then we can move the 500 over to the right-hand side, and sure enough, we just actually end up with the constraint. Maybe that's an easy process to do right away, but this Lagrangian allows us to take the whole system of equations and turn it into just one vector equation. Now, when you see a system of equations like this, you'll also notice that they are nonlinear. It can be a bit of a challenge to solve this whole system of equations. So try to start with the easiest one, especially factor it and set it equal to 0 so that you can narrow down the cases. From there, you can carry those solutions through the other equations. And you may be able to throw certain cases out immediately because they cannot potentially get us a volume of 500, or you'll just know right away that it's not possible that that would be a minimum surface area. So let's try working with equation 2 since it seems to be the easiest one to work with initially. With equation 2, there are a couple potential solutions. We can see right away it's possible that r equals 0, or it's possible that lambda r equal to 2. Now, r equals 0, we can throw that out immediately. If the radius equals 0, then we could not possibly have 500 milliliters of volume. We'll throw that out. And we'll just work with lambda r equal to 2. Now, you can solve that for r and substitute into a couple equations, or you can solve for lambda and substitute into equation 1. Although you'll also notice that equation 1 actually has lambda r right in it. So maybe we'll just leave that as is, and we'll substitute into equation 1 immediately. In equation 1, we're going to remove that lambda r and replace that with 2. Now we have an equation that just involves r and h, and we can continue to simplify, and we'll see that we must have that h equals 2 times the radius. And that should certainly give us a unique solution to equation 3 now. Plugging h equals 2r into equation 3, we must have 2 pi r cubed equal to 500. That's not going to be a very nice number for r, but we can solve for r and get r in terms of centimeters. 4.301 centimeters, because 1 milliliter is equivalent to 1 cubic centimeter. Tracing our steps back, we know what our height has to be. Height is equal to 2 times that radius. Now, barring a little rounding error there, h is approximately 8.602 centimeters. Now, of course, if you go and measure a beer can with 500 milliliters volume in there, that might not exactly be the correct dimensions, but then you have to imagine that the manufacturing process and assembly of the can isn't exactly the same straightforward process as a perfect right circular cylinder. There's additional aluminum in various parts of the can, and it's also really difficult to take a sheet of aluminum and punch circles out without wasting some other material. So that might not be the best way to optimize the minimum amount of material, including the wastage, but it still allows us to see a pretty good application of optimization for functions of two variables. Let's try an example where we're looking at optimization of a function of three variables now. Well, now that we've done a minimization problem, let's take a look at a maximization problem. In this case, we're going to try to find the dimensions and volume of the largest box that can fit within an elliptic paraboloid where the bottom of the box lies on the xy plane. Now, you might want to at least remember that this elliptic paraboloid is opening downwards from z equals 25 downward towards the xy plane. And so that gives us a dome shape that we're fitting this box inside of. And you might not need to get a very good sketch of the elliptic paraboloid with the box inside of it, but having a basic idea of that shape might at least allow you to come up with the objective function as well as the constraint function. As far as our elliptic paraboloid goes, starts at the value of z equals 25 and opens downward, leaving us with a circular base. Now we need to try to fit some kind of box inside of that dome, so we can't let the base of the box take up the entire circle. We'll have to shrink it in a little bit so that we can give it at least some height before it bumps into the dome. Now, if we're going to try to make this box as big as possible, you can imagine that these vertices here at the top of the box are going to bump into the wall that is our red surface. So let's just pick this point here, being the point x, y, and z. What is the volume of this box going to be? That's our objective function. Now, if we're letting x just be the x coordinate of that vertex, then the total depth of this box is going to be 2x. Similarly, if y is the y coordinate of that vertex, then the total width of this box is going to be 2y, and the height of this box is simply going to be z. Putting all of that together will give us a volume. We'll have 2x times 2y times z. That's our function that we're trying to maximize. F of xyz is 4xyz. Now, the constraint is that that particular coordinate, xyz, is also on the surface z equals 25 minus x squared minus y squared, so it has to satisfy that equation. And let's put that in the implicit form, g of xyz equals k. In this case, we could write that maybe as z plus x squared plus y squared equals 25. Now we've got our objective function f and our constraint in implicit form. Let's try the method of Lagrange multipliers by setting up the Lagrangian. In this case, the Lagrangian is going to have four variables, x, y, z, and lambda. We'll start by constructing it using the objective function 4xyz, and then we have minus lambda times our constraint. At this point in time, we just need to set up the system of equations. So we'll start by letting the gradient of this Lagrangian equal to 0 vector, and that will give us four equations for each of the four variables. The partial derivatives with respect to x, y, and z, and then the partial derivative with respect to lambda. And when we take the partial derivative with respect to lambda, we know that that can easily just be simplified into simply the equation of our constraint, in this case the elliptic paraboloid itself. And the three other variables, x, y, and z, those partial derivatives are all set equal to 0. You'll notice that those three equations really use pretty much the full palette of all four variables, so it's a little bit difficult to maybe factor and work with different cases for solutions of x, y, or z. Instead, what I would maybe suggest for these first three equations is, since they all involve lambda, why don't we solve all three of them for lambda and set all of those expressions for lambda equal to each other. So for instance, if we take that first equation, solve for lambda, we'll get 4yz divided by 2x equals lambda. And we can simplify that. Lambda is just equal to 2yz over x. We'll do that again with the second equation. We'll see that we get 2xz over y. Finally, with the third equation, if we solve for lambda, lambda is just equal to 4xy. Now those three expressions are equal to each other. If we just take a look at a pair of those expressions, then we should be able to set them equal to each other and hopefully simplify and get some expressions for x, y, or z. Let's start off by taking a look at the first pair of expressions. If we have 2yz over x equal to 2xz over y, then you can see we can cancel a 2 from both sides, but we're also easily able to cancel z from both sides. Maybe just think about that for a second, because we're looking for a maximum volume. If z was equal to 0, we would certainly get a minimum volume. We're going to assume that z is not equal to 0, and that allows us to divide both sides of the equation by z. Well, that'll give us y over x equals x over y. Of course, again, x and y cannot equal 0. We can simplify that, and we'll get x squared equals y squared. Now, there's a lot of different solutions for that, but let's specifically take a look at that vertex x, y, z that's on the elliptic paraboloid. I think we can safely assume that we really only need to find that one particular vertex in the first octant. So let's just assume that x, y, and z are all positive. If that's the case, then we should be able to just simplify to just x equals y. Well, that's good. We can make at least a substitution for y and maybe get x now. But let's get rid of one more variable by taking a look at another pair of expressions, maybe 2yz over x and 4xy, and set those two expressions for lambda equal to each other. In this case, we can cancel a 2 from both sides, and since y is not going to be 0 for a maximum volume, we can cancel y from both sides. That'll give us z over x equals 2x, and that allows us to make a nice other substitution, z equals 2x squared. Now that we can replace y with x, and we can replace z with an expression of x, we should be able to get one equation only involving x at this point in time. We just need to take a look at that fourth equation, which is the elliptic paraboloid. Starting with z equals 25 minus x squared minus y squared, we're going to make a substitution on the left-hand side for z equals 2x squared, and on the right-hand side, another replacement, y equals x. We can collect terms from there and get 4x squared equals 25, and that results in x squared equaling 25 over 4. And that's nicely a perfect square as well. Again, just thinking about only the first octant where x, y, and z are positive, this allows us to get a solution. X would equal 5 over 2. Since y is equal to x, y is also equal to 5 over 2. That gives us a square base, which you might have been able to sort of predict from this particular picture. And finally, if z is equal to 2x squared, then z must equal 25 over 2. And there's the vertex. What about the dimensions? Remember that the width, the depth, and the height of this box aren't exactly x, y, z. The depth of the box is actually 2x. The width of the box is 2y, and the height of the box is in fact z. All put together, that gives us a volume of 5 times 5 times 25 over 2, for a volume of 625 over 2. Well, now that we've got the solution, let's just take a moment and kind of visually remind ourselves how the whole method works and why those gradient vectors are parallel again. So in the first time that we saw the sort of visual explanation of the Lagrange multipliers, well, you got to remember that we had a function of only two variables, and if that function was equal to a constant, that was like a level curve. And the actual constraint itself was in the same form of a function of two variables equals a constant. So that's basically also a level curve. And at the optimal point, those two curves share the same tangent line, in which case their gradient vectors must be parallel to each other. But now we've got functions of three variables. And if we have a function of three variables equal to a constant, well, that's a level surface. So it's a little bit tougher to visualize. We're not going to be able to use Desmos for this one, so I'm going to go ahead and turn to Maple and see if we can visually see how these two gradients are still parallel to each other. So here I'm going to have, of course, width plots so that we can do some interesting plotting tools. And I have the student multivariate calculus package, which provides the Lagrange Multipliers command. Well, obviously, that's going to be helpful. We've got the function that we're trying to maximize, which is volume 2x times 2y times z. Next, we have our constraint. Now, this is the equation of the elliptic paraboloid, where g of x, y, z equals z plus x squared plus y squared minus 25. I've set that out specifically so that when I set g equal to 0, I get the constraint. That allows us to use the Lagrange multipliers command, and we just provide the objective the constraint, and our variables. Now, you could actually also provide more than one constraint because, as it turns out, if you have two or more constraints, then we simply have two or more Lagrange multipliers. And when we run that, we get quite a few solutions, far more than just the one that we got. But you can see that a lot of the first bunch of solutions here will throw right out. They won't give us a maximum volume because either x, y, or z is equal to 0. So we just disregarded all of those. These final four solutions are the same values, but in four different octants. And if we're only trying to focus on x, y, and z positive, you can see we get the exact same solution by hand. Now, it doesn't tell you what the maximum value of the function is. You'd have to pick one of these points and substitute it back in to get the actual volume. But what about seeing those level surfaces? Now, I've tried to make a little bit of an animation here, but I've already provided it, so I didn't have to run this again because it took quite a while to actually generate this. And as it turns out, I think this file got to be a few hundred megabytes large. Now, here, I'm going to back this up to here. You can see 4xyz is equal to k, where k is 6.25. That's a pretty small volume compared to what we're supposed to be getting as our maximum 625 over 2. That's a weird looking level surface, but that blue surface there is actually the surface corresponding to the equation 4xyz equals 6.25, or 25 over 4. Now, as I increase k, I should be pushing that surface farther away from the origin and push it all the way up to the last frame of this animation. You can see that they are just touching and they are actually tangent to each other. And at those particular points where you see, maybe in the first octant, there's a point there, that is the optimal solution. That's the vertex we were looking for. Now, of course, the animation takes a very long time to play through again, so let's just display what that box looks like. Here is all of the sides of the box, as well as the elliptic paraboloid, all put together. There we go. Those are those two level surfaces, the blue and the red, and at that particular vertex, that is where we form the box. Now, as you can see, it just barely fits inside the elliptic paraboloid, and it's as large as possible. The bottom of the box is on the xy plane, and it has a volume of 625 over 2. Now, of course, it does look pretty much exactly like a cube, but you can see that the axes here for x, y, and z are not to scale. What this actually looks like in one-to-one is it's about as tall of a box as we can possibly fit under that dome. We could have gone wider, but we would have lost height very quickly. So this is the optimal solution. All right, well, I think I'll wrap up our Lagrange multipliers with that note. And maybe if you're interested in this optimization using Lagrange multipliers, keep in mind that we could throw more variables into the problem and maybe not necessarily visualize a problem, but still solve it using the same method. And with more variables, we could have more constraints. For instance, with 3 variables, we could potentially have 2 constraints. And at that point in time, you have to try to understand the relationship between the gradient of your objective function and the gradient of your constraints. But there is still a relationship. You just end up with multiple Lagrange multipliers. So I'll leave that there as a bit of a way for you to explore on your own a bit for now. Thanks for watching, and I'll see you in the next video.